Welcome to Tera Cheating. My name is Timothy Lattis, and this is the Neo-Kino Graphics channel. We're going to talk about the quest for the biggest marketing number. For example, when both NVIDIA and AMD added sparse wave matrix multiply accumulate, they count the explicitly known and explicitly skipped zero terms as extra teraops. This is how they double the marketing number, while the hardware actually can only do half of that. This is a great example of corporate numbers lying. We also have a great example of professional derping. Digital Foundry and another user noted my PS5 Pro specs are all wrong. How about we dive in even more detail and look at the aspects of instruction perf? My fail for not representing numbers correctly. I just blind copied the data from Wikipedia without fact checking. For those who know my professional background, this is even more embarrassing. So ALU perf can be hard to eyeball these days. It doesn't easily reduce to one number on recent hardware. You cannot necessarily trust numbers from online sources, such as my videos. Different operations can have non-obvious throughput and costs. Let's start by talking about Ampere. This is the chipset family in the Switch 2. Demystifying NVIDIA Ampere architecture through microbenching and instruction level analysis. This paper takes a look at A100. You notice they have a great table. The table gives instruction clock cycles for various instructions. You notice that some of these are very complicated. If you look at the SAS, which is the disassembly, you'll see multiple instructions for a given PTEX instruction. There's certain very interesting callouts in this list. The first thing is that 16-bit ops can be quite expensive, as many of them look to be emulated. Now, I don't know if this is just single 16-bit op or they were doing vectors or so on. I don't know if the due diligence was done there. You know, some of them are more than just two instructions for emulation. Another big thing here is bit field extract and bit field insert. These are on 32 bits and they involve a tremendous number of instructions. So while Switch 2 is Ampere, if you look at the marketing fluff stuff, you're completely missing the full picture. And note, there could be chipset differences between the handheld version and the larger compute version. Some ops can be quite expensive on one and potentially not on the other. It all depends on architectural specifics, which we don't have because we're not under NDA. Now let's move on to a more open architecture, RDNA 2 versus RDNA 3. Chips and Cheese, they're a great source of all this information because they actually do microbenches. So RDNA 2, they offer single issue FP32, and they offer single issue packed FP16. So the 16 gets an effective double rate even though the instruction rate is the same as FP32 because it's doing two operations in one. RDNA 3 added some dual issue FP32 ops. However, they did not dual issue the FP16 times 2 ops. So FP32 got a little bit of inflation and FP16 stayed the same per clock. You can see this in Chips and Cheese benchmarks, which brings us to a very interesting problem. The idea of slop versus optimized code. So when looking at RDNA 3 versus RDNA 2, ISVs that did not optimize and used FP32 for everything might get rewarded. There might be a possible uplift. However, those who squeezed every last drop of performance out with explicit pack 16-bit, they might not see any improvement other than uplift in CU count and clock rate. So when the vendor says, oh yeah, our SMs or our SIMD units or our CUs are so much more efficient, that doesn't necessarily mean that efficient code is going to run any better. Hardcore devs can look at hardware specs with a different translation dictionary, i.e. from the perspective of running already optimized code. So when we look at RDNA 4, AMD makes some interesting claims. They say peak half precision vector performance is double peak single precision vector performance. Well, so we know dual issue FP32, i.e. FMAs, is going to get double rate because RDNA 3 already had that. However, dual issue FP16 times 2, or the packed instruction, that would be quad rate at this point. That would require dual issue of these VPAC FMA F16 ops. This starts to smell like false advertising. The reason why is if you look at their instruction set architecture, we have a problem. RDNA 3 and beyond only gets dual issue in Wave32 mode with what is called a VOPD op. These VOPD ops are explicitly encoding two operations in one instruction. Now note, Wave64 mode does not use this. It can get dual issue using something different. Now if we go through the ISA guide for RDNA 4, you'll notice that the instructions don't have anything that has 2x FP16 FMAs. So we know Wave 32 can't quad issue 16-bit ops. And note, .2 ops don't count because they accumulate into FP32 destinations. So one would need extra FP32 to FP16 conversions, which are not double rate, for the next operation, thus nullifying any benefit. Luckily, somebody on Twitter actually ran the benchmarks. And that evidence points to, yeah, AMD is lying about RDNA 4. FP16 and FP32 peak at roughly the same rate, and thus the hardware does dual issue FP32, but it only single issues packed FP16. You'll also notice that some of the FP32 results don't quite meet up to the FP16 results. And that is because not all code gets good dual issue rate. RDNA 3 and above has a lot of issue restrictions on dual issue. This is a list here. I'm not going to itemize them for you. You can just read them. So some people are probably wondering, why is 16-bit a huge deal? Why do I make such a big point out of it? After all, most devs don't even bother optimizing with 16-bit. However, when one has a large working set, one needs packed 16-bit simply to fit inside the register file with enough occupancy to hide the latency. This is especially the case for things like post-processing. We're using large filter kernels. For example, a 4x4 texel neighborhood takes 64 VGPRs at 32-bit float. This is also true about a bunch of other algorithms besides just post-processing. In fact, everything I've done in the past few years has required 16-bit to run fast. So platforms with double rate 16-bit over 32-bit have some big advantages in ALU-bound workloads. And note, when I say double rate 16-bit, that means all 16-bit ops, not just FMAs. Things like min and max matter a lot, especially in post-processing, for example. So now let's go back to that chart that I made before with all the platforms and potential future estimates by Moore's Law is dead. And let's expand it. So this time I have put the platform down with the clock rate, the CU count, followed by the physical SIMD size, which might be, say, 16 or 32, followed by the number of SIMDs, physical SIMDs that is, followed by the number of ops in the instruction. So notice an FMA gets 2 ops in the way it's accounted for, followed by the number of instructions that can be issued at the same time, peak on the hardware. So in this, the Steam machine actually looks incredibly powerful if you compare it to, say, a PS5. That's because it's getting dual issue. This is a very blind way of looking at the performance. Also notice that the Steam machine looks insanely powerful compared to the Steam Deck. Much more powerful than actually in practice. And of course, we're not looking at memory here. We're just looking at the ALU. Another way we can look at the hardware is to actually look at it from a perspective of doing 2-op in 32 ops. So in this case, I kind of darkened the switch 2 area because I have no idea what they're doing, to be honest. For instance, on AMD, you have V shift left add U32, which is doing a shift and an add. So I count that as 2 ops, kind of like an FMA. So now you notice the areas highlighted in red, these don't look quite so fast anymore. So if we compare a Steam machine to a Steam Deck, it's only a 5.5x increase in the number of 2-op and 32 ops, because these are not going to be dual issued. And this is actually a lot more reasonable, or more of what's actually expected from benchmarks, at least in the Steam machine and Steam Deck case. Another note here is if we look at RDNA 4, it doesn't necessarily look as fast as you'd think. For instance, the 97EXT is only 1.4 times the peak spec of the PS5 Pro. So if you were to have a post-process that's severely optimized, it might not be all that much faster on modern hardware. So here's yet another view, this time thinking about packed FP16 ops. You'll notice that there's now 4 ops per instruction because we're talking about the VPK FMA F16. It does 2 FMAs and that's 4 ops. I also darkened the switch too because I don't know enough about that hardware to say anything. And now you'll see some very interesting comparisons. For instance, if we compare, say, the Steam machine to the PS5, PS5 now has higher capacity, 1.2x of what could be done on the Steam machine. That's thanks for the fact that PS5 could do double rate FP16. Also, if we look at RDNA 4 and RDNA 5, assuming RDNA 5 is the same as RDNA 4 with the respect to dual issue, you'll notice that the leap between, say, a 97EXT and a PS5 Pro doesn't look all that big anymore. Another interesting thing here is if you look at the original Steam Deck, the fact that it gets packed FP16 could be huge. Another issue here is compiler problems. Many coveted platforms have optimization bug workarounds, for instance in STP. You can see some of the things that had to be done. Had to turn off the INF optimizations, had to turn off the 16-bit reductions and default to 32-bit, had to switch to group shared or LDS instead of using WaveOps. Another problem, hardware bugs. This is just one example. If you look through the LLVM stuff, this one I think would be affecting RDNA 3. The fact that inline constants are broken, that's kind of scary bad. Basically means that the vendor's not actually checking the hardware that well. I mean, this follows from, say, not putting super optimized stuff into your basic testing. This ends in an ask for GPU vendors distracted by the AI bubble, i.e. all of them. Important shader SIMD side stuff is getting ignored while you maximize the future WMMA heatsink area. How about not abandoning basic shader performance issues? Alright, so we'll close out here. And note the paperclip maximizer is already in full force. Until next time.